Good afternoon all, and welcome to this webinar. This webinar on recent innovations and limitations in measurement in partial discharge and rotating machines. And this webinar is brought to you by Vhf and Ice Power from Coil. I would like to remind you to ensure the volume is turned up on your device and ensure that you have a stable internet connection. This will ensure that your streaming and audio will run smoothly. Attendees can ask questions via the question panel, which is located within the GoToWebinar control panel. And by default, the control panel is located on the right-hand side of your screen. The chat function is reserved to webinar organizers to communicate with the attendees. Attendees will not be able to chat to each other, but however, they are encouraged to ask questions. A recording of this presentation will be made available on SAIEE YouTube channel, SAIEE TV. And a recording will also be made available on the SAIEE website under Events drop-down menu in the section of Past Events and Webinars. A certificate of attendance will be issued a few days after this webinar. I'd like to present Greg Stone, a world leader and developer and specialist in partial discharge from Ice Power, a motor and generator monitoring company that he helped form in Canada. Greg, you ready? Want to take over?
Yes, I am. So Minx, I guess you have to give me the control. Aha, show my screen. Okay, so I hope Minx or Neil that you can see my screen now.
Yes, we can do.
Peachy. Okay, well, thanks very much, Neil, for that introduction, and thank you for all those who are attending this webinar. I had actually hoped to be in South Africa and do this thing live, plus some other seminars last April, but of course, the COVID virus intervened and it's completely changed my life, and I'm no longer flying anywhere. I'm absolutely devastated because of that. I want to thank the South African IEE for hosting this and providing the platform for this webinar, and of course Vhf, who we've long been associated with, for sponsoring the webinar. This is going to be talking about partial discharges, partial discharge testings on rotating machines. That normally means the stator windings. And rather than just a pitch on one particular technology and stuff like that, and I'll kind of cover some of those things, I also like to talk about limitations, okay? There's no perfect technology in this world, and there are limitations, and I think perhaps many of you in the past have seen my presentations when I've been lucky enough to come down to South Africa. And you probably heard all the standard stuff from myself or others about what partial discharges are. So I'm going to kind of skip over that, talk a little bit about the current state of the art, and then carry on and talk about limitations and various things like that. Okay, so of course, there seems to be a problem. I'm having troubles forwarding, but hopefully it'll eventually respond. Maybe, yes. Aha, it's worked. Okay, so this is what I'm going to be presenting. I guess I should give a little bit more of a background on myself for those who are not familiar with me. But for the first third, I used to say first half, but now I guess the first third of my career, I worked for a company called Ontario Hydro, now called Ontario Power Generation. We're a Canadian, or it's a Canadian utility. At one time, it was the largest electric power utility in North America. And eventually I became responsible for the testing of the motor and generator, rotor and stator windings. Okay, and also doing visual inspections. And of course, there were completely other different teams who did various engineering and maintenance aspects. Along the way, I was fortunate enough to be able to do a lot of research that was funded by the North American utilities to investigate PD. And in 1990, I helped form the company called Iris Power. And as Neil said before, we make a wide variety of condition monitoring equipment for rotor and stator windings. Okay, so we're focused on the windings. We're not just focused on PD everywhere. It's other stuff. Okay, so I'm gonna, as I said, I'm gonna give a little bit of a brief interview into what is PD, or review of what is partial discharges, particularly in stator windings. I'm going to very quickly overview some of the deterioration processes, and it upsets me to have to be so brief on this because, in fact, that's what my research into over the last 30, 40 years is to try and understand why rotor and stator windings fail. So I'm only going to be able to spend a few minutes on this now. I'll then talk about way back in the beginnings of time when PD testing was first introduced for motors and generators by Westinghouse, talk a little bit about the state of the art, and a lot of that involves dealing with the issue of noise. When we're talking about online detection, that's PD detection during normal operation, we're talking about when the machine is connected to the power system, and that means there's a lot of noise as possible. So I'm going to talk about the current state of the art for separating that stator PD from other types of electrical pulse signals. An update on interpretation, what information you can get, what you cannot get, where we still have some uncertainties. And then I'm going to deal with certain credibility issues, limitations, if you want, of online PD testing. There's a lot of commercial voices out there, a lot of vendors out there claiming it'll solve all the world's problems. And after 40 years or so in this kind of technical field, that's just not true. And so I want to point out some of these issues and talk about at least where our organization is taking us into the future with PD and associated condition monitoring equipment for rotating machines. If I have time, and I should have said in the beginning that nominally this is set for about an hour and a half, after which I hope we'll have quite an extensive 30-minute or so Q&A session, so make sure you ask those questions as we go through. But if we have time, or maybe if I don't have time, but maybe it'll come up in the questions, it's just talking about low frequency versus very high frequency PD detection. There's the world's kind of split in two. We're one of the few companies that actually do both. So I think we can be pretty unbiased about that particular aspect, and so I can share some of my opinions, because that's what they are, on low frequency versus very high frequency PD detection. And again, EMI, that's electromagnetic interference, sometimes called RF monitoring or electrical signal analysis. There's all sorts of different names. It was quite widespread used in the 1980s. Now there's only a couple of organizations out there who are really doing it, but I think some of them are in South Africa. So if we have time, we'll talk about that, because I don't see them really as competing technologies, more as complementary technologies. And conclusions at the very end, hopefully I'll remember to leave the references. There's some good references, certain standards that I won't be referring to in my presentation, and some books out there that I think might be relevant to you. So that's what we're going to be addressing over the next while, and I hope you can understand my accent. And remember, for those of you who've met me before, please do not call me an American. I come from Canada. Okay, so I know many of you who are participating here are fairly familiar with, or very familiar with partial discharges and rotating machines, but my experience in doing these webinars over the last few months is that there's always a reasonable percentage of people who are kind of new to it. And so I'd give a little bit more background than just focusing on the PD. And so here what you see is the stator winding, okay, or a stator of a large motor or perhaps a small generator. I'm doing this mainly for terminology here. You'll hear me talking about the slot area of the winding. This is where the stator core is. And of course, that's the laminated steel core. In that core, we've inserted inverted coils that go around and form a loop for obvious reasons to make the motor or the generator work. But failure processes and PD detection is somewhat different between what happens in the slot and what happens in the M winding. This is the area outside of the stator core that I call the M winding. It's actually the non-productive part of a motor or generator. It's just there to make physical connections and to allow some reasonable support of the M windings. But I just wanted you to hear that because I know with my Canadian accent, end winding seems to come out as M winding, and that's not what I mean. Now, if we take a cross section through the stator slots here, the area within the stator core, where slots are punched into the steel, what we'll typically find in almost all machines, certainly machines 2400 volts and above, is that there's two coils in each slot. Okay, now the rotor would be down here. So think of this as a cross section taken up here. So the rotor would be down here. I'll call this the top coil. This is the bottom coil. And if we take a cross section of what's inside there, we'll see the copper conductors. If it's a multi-turn coil, we might also see strand insulation and turn insulation. And of course, we'll have our high voltage insulation around here. And that high voltage insulation is what really is normally the focus of PD testing. We can't detect problems in the turn insulation, especially between the turns in this region. I'll mention this later again. Our focus with online PD tends to be this high voltage ground wall or main wall insulation. And literally for the last 50 or 60 years, it's been made primarily of mica tapes, mica paper tapes, that are wrapped around the copper conductors and that are then impregnated normally with epoxy. That's what the most common material is today, where the epoxy glue those mica tape layers together. And the reason why that's there is because, of course, this copper is at high voltage. If it comes in contact with the stator core, which is at ground or earth potential, you'll have a phase to ground fault. Okay, and phase to earth fault. I've got to be bilingual here. And so what happens is, of course, your motor or generator would trip out. So we don't want that to happen. And so our focus here is going to be on this coating because what happens is, it's because of the epoxy content, it's an organic material. It's just like a human being. It will gradually age over the years and become less effective at being a good electrical insulation. And really and truly what we're doing with online PD or offline PD is detecting that aging, okay? Because PD is quite often a symptom of the deterioration of the stator winding insulation system. In addition to the strand and turn insulation and of course the ground insulation here, we also have on machines usually 6 kV and above, although there's differences for variable speed drive machines. That's a separate different topic that we can maybe address some other day, because there's a lot of issues now with motors that are fed by drives. But we have the semiconductive coating in the slot. This is just a carbon-loaded or graphite-loaded painter tape on the surface coil to prevent surface PD. So I'll come back to that a little bit later. But this goes by very many names, including OCP and conductive coating and many names. Okay, so I wanted to let you know about that. And of course, there's wedging and side packing and things to keep the coils tight in the slot in a non-global VPI machine. Okay, so with that brief introduction to the stator winding insulation system, I want to now just give a tiny introduction to what is partial discharge. As we'll see a little bit later, what happens with partial discharge is if you have a perfectly manufactured winding and with only the copper conductors and perfectly made ground wall insulation, and that coil insulation surface is in perfect contact with the stator core in this region here, there will be no partial discharges, just like there's normally no partial discharges on high voltage cables. Okay, but the reality is, because of various manufacturing issues, or in fact more commonly aging of the insulation, what happens is one gets voids, and that's what this black area here is. That's a void that occurs because of manufacturing or aging, and I'll discuss that a little bit later. Those voids can also be right at the surface of the copper, okay? Or they can be between the surface of the ground wall insulation and the stator core here. So they can be anywhere throughout between the copper and the stator core. And the whole idea is if we do have this air-filled void, which we'll talk about how we might get that later, it turns out a very large voltage builds up across there. Now, normally we use finite element electromagnetic field plotting techniques to do it, but those of you who've got an electrical background will remember, and maybe even some of you mechanical guys will remember something called capacitance or electrical capacitance. And so there is an electrical capacitance, okay, between the copper and the top of that void, and I'm representing that here. There's actually an electrical capacitance of this void itself, that's this capacitor, and there's capacitance between the bottom of that void and the surface of that coil where ground potential is, okay, and that's this capacitor. And if you think about it, if you just draw a line straight through there, and if you recognize, say, for example, if this is an 11 kV machine, that's phase to phase, that's 6.3 kV phase to ground or phase to earth, what happens is there's going to be 6.3 kV across these 3 series connected capacitors. And we don't have the time for it here. Go on Wikipedia, read my books, go and look at the IEEE standards, or just go on Wikipedia probably, and you'll see very detailed calculations just using electric circuit theory that shows that if we know what these capacitances are and we can estimate them, okay, and or measure them, that it turns out a large voltage, a large capacitive voltage will drop across here. In fact, it's about 1/3 of the voltage between the copper and the core. And that really means that it's, say, if this is an 11 kV machine, that means that 6.3 kV in the line end coil, this is at ground, 0 volts. That means there could be 2,000 volts across this little airspace. And then the next thing that happens is if there's a high enough electric stress, okay, in other words, a high enough voltage per unit distance across here, there will be electrical breakdown, which is really just a micro version of lightning between a cloud and the ground, okay? It really involves a process called electrical breakdown, and the electrical breakdown strength of air is just a small fraction. It's less than 1% of the electrical strength of the epoxy mica itself. So the epoxy mica is 100 times stronger than that of the air. Now, obviously, I'm making certain broad statements here. There's a lot of devil in the details, but hopefully this is meaningful. So the idea is there'll be a high enough voltage across here that you'll get a spark here. It's only in that void. It is not in the solid insulation because the solid insulation is 100 times stronger. And so there's electrical breakdown. And what electrical breakdown is where you essentially rip electrons, the outer electron in an atom or a molecule, especially a gas molecule, where because of the electrostatic forces, basically you're able to rip the electrons away from the atoms, okay? And those electrons, if this is, for example, positive at this part of the AC cycle, those electrons, which are negative, will flow across that void. And it will create, because we have charge moving through space and time, a current, I equals dq by dt if you've got an electrical background. And so every time there's a discharge, it creates a current pulse. And this is what we're measuring. If there was no void, there would be no discharge and the winding's good. Everything's cool, okay? But if there is voids, either because of manufacturing or normal aging during in-service, what will happen is we'll get these things called partial discharge. And we call it a partial discharge because it's only in the void. A complete discharge would be between the copper and the stator core, and it would break down through there. Of course, that's an earth fault, and the motor or generator would trip. Okay, so hopefully this is meaningful. So what happens when we do have these voids, which are a symptom of aging or manufacturing problems, we'll create PD. Ideally, there would be none there. And those discharges then can be measured because they give rise to currents. And therefore, then we can detect, without having to look inside the machine, that there's actually defects within the machine. So think of it, me, I'm an old man, I've got lots of wrinkles, I've lost my hair, blah, 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 but my wrinkles are an indicator that I'm an old person, okay? And anyone looking at me would instantly recognize that I'm an old person, which is why I'm not showing my face right now, okay? And so the idea here is that when these voids are created, they're like wrinkles occurring in a person. It's an indicator that things are not going well. Now, I don't fail normally because of wrinkles, okay? And windings, unlike most other types of equipment, usually do not fail because of PD alone, okay? Usually something else has to go there. So that's your intro to PD. And that for me was an amazingly short presentation. It took me 2 full courses when I was doing my PhD studies to truly understand what PD is. Okay, so I said when we have a discharge, what happens is currents, or electrons rather, are flowing towards the copper or away from the copper, depending on the relative polarities. And here are examples of pulses. Now, these are actually measured on 800 megawatt generators during normal operation. I'll explain how we measure them a little bit later. But here, for example, all this is an oscilloscope trace. And you can see that the time base is 10 nanoseconds per division. So this rise time here is really only 3, maybe 4 nanoseconds. That's a machine, this is a machine operating in air. If it was in hydrogen, it would be less than a nanosecond for various technical reasons. In high pressure hydrogen, the PD pulses are much, much shorter. But you can see the duration of these pulses are less than 5, 6, 7, 8 nanoseconds. And this is going to become very important to us when we talk about PD, because every time there's a discharge, that creates that current pulse, and that will travel through the winding via various mechanisms. Okay, now the vertical scale here is millivolts, and yet I said PD creates milliamps or amps, or it's a current. Well, unfortunately, Tektronix oscilloscopes don't measure current, they measure voltage, but we as electrical people, we know if we put 1 milliamp current through a 50 ohm resistor, we have something called Ohm's law, V equals IR, and that 1 milliamp of current through 50 ohms will create 50 millivolts. In fact, I use this example completely exactly because this is actually a 50 millivolt pulse, which means it's a 1 milliamp pulse current. Okay, so we're going to come back to these pulses a little bit later because this is going to be important to us for how we measure PD. Okay, so well, I forgot this slide was in here, but this current pulse, there's lots of ways we can detect PD, especially if we're doing offline tests. But every time there's that spark or that discharge, there's a current pulse is emitted that actually will travel through the winding to the machine terminals, which is where normally we'll detect it. There's also radio frequency emission. It gives off radio waves, and anyone who's familiar listens to AM radio and you're far away from a city and you drive under a transmission line through the snow, well, that's not likely for you, but under the rain or foggy conditions, you can hear that corona or that partial discharge occurring on your radio, in your AM radios. And this is also the fundamentals for EMI monitoring, if we have a chance to get into that a little bit later. It also gives off light, mainly in the ultraviolet region, but of course you can only see it if it's on the surface of the coil, and of course the machine is open. It also creates, just like lightning, it creates sound, acoustic energy, again, mainly in the ultrasonic region, about 40 kilohertz or so. Again, we'll only detect it if it's on the coil surface. And for air-cooled machines, okay, so that's almost all motors, all generators, and all hydro generators, and most small or less than a few hundred megawatt turbo generators, if we're in an air environment, that discharge will create ozone. Okay, that's O3, and that in turn, with humidity and a little bit of nitrogen in the air, creates nitric acid, and so there's chemical signals given off by partial discharges, again, only if it's on the surface. But I'm only going to talk about electrical PD detection in this one because the focus, because of time, is on online testing. Okay, so we talked about PD, a little bit of how to detect it. We'll get into more details later. Okay. Why would we want to do it? And it's because PD testing is a symptom sometimes, but more commonly a cause of various aging mechanisms that can occur in stator winding insulation systems. It can also detect things like arcing and sparking because of poor electrical connections. But primarily it's used to detect the aging of the stator winding insulation. Usually on machine 6 kV and above, you'll normally get at least 2 years heads up between the onset of high PD and when you might get significant amounts of deterioration. And of course, the real purpose of online PD testing or even offline testing is to detect, without having to dismantle the machine, that aging of the insulation is occurring, so that then one can then proactively on the machines with high PD go in and do proactive maintenance. So it's the essence of predictive maintenance, or what some people call condition-based maintenance, doing maintenance based on signals that are on monitors that are telling you something's going wrong, as opposed to just going based on a calendar, okay, or past statistics of when you should open up that machine. So the failure process that we can detect are these. I don't have a lot of time to talk about this. You'll see one of the references at the very end is IEEE 56, which goes into a lot about these failure processes and the various symptoms or characteristics of these mechanisms. And I'm going to show you a few pictures a little bit later, but I think in the intro to this presentation, I said, hey, we want to talk about the things that PD testing can't do, you know, where some overclaiming has occurred in the past. And it turns out, although these might represent the most common of the 25 or so failure, if you read my book, the 25 or so failure processes that can occur in stator windings, okay, and these are by far the most common ones, some of them caused by manufacturing, some caused by aging and service. Okay, there are some important failure processes we can't detect. Probably the most important is unwinding vibration, unless you're right at the end of life. So remember I talked about the coils outside the slot. If they're vibrating, they do not produce PD. You have to detect them some other way. And unfortunately, unwinding vibration is a huge problem right now for a lot of turbo generators, air-cooled turbo generators made since about 2000 to about 2014 by virtually most of the world's manufacturers. These would be air-cooled machines less than a few hundred megawatts. Okay, there's a big unwinding vibration issue right now. One insurance company says 50% of all the money or claims they paid out has gone to unwinding vibration of the stator windings. We can't detect that with PD, so obviously that's why we are also into unwinding vibration sensing. It can't detect turn-to-turn insulation. There turns out there's not enough voltage there to cause this electrical breakdown process. So if you have problems between the turns, the voltages there are too low to detect PD. Okay, water leaks, if you have direct water cool windings, again, I know people have made claims that they can detect with PD, but we've seen no evidence. And we've got our stuff on probably 3,000 or 4,000 direct water cooled machines, and we've seen no correlation with minor water leaks that happens with certain brands of machines. If you have metallic debris and it's not on a high voltage coil, we won't see it. So if you leave a wrench in the machine, that's one of the biggest failures I had when I was in a utility. We had the 600 megawatt unit go down because we left a tool inside the machine. No monitoring system could have detected that, and the machine failed quite catastrophically. Okay, but unless it's you're lucky that it's on a high voltage coil, you won't detect it. And even complete gaps right down to the copper in the insulation away from the high voltage coils, online PD detection will not detect it. Now, offline testing might detect these latter two problems, but I want to point out what we can't detect. So you can't expect PD to tell you everything that goes wrong any more than a blood test can tell you every possible disease is happening in your body. The technology just isn't there. The science just isn't there. But let's look at some pictures. These are ones that I've been showing for a few years, and so they'll be made available to you later on if you're not recording this yourself. Okay, but these are problems for photographs from 4 different machines that are really where there were manufacturing problems. It gives rise to PD because PD includes electrons and ions that bombard the epoxy insulation. Eventually, it'll cut a hole through that insulation. You'll get a process called electric treeing or electric tracking. And given enough years, usually well more than 10 years, sometimes 20, 30 years, that PD will eventually eat a hole through the insulation, the ground wall insulation, and cause a failure. But the process is very slow, and it's very slow because of that mica I told you about. Mica is one of the most PD resistant materials known to mankind, and within reason, we can always withstand certain levels of PD. For as long as there are some machines in my old utility that are still operating, and they still have some what I would call significant PD, but it's just a pure PD mechanism, still hasn't caused failure. This is here's the stator core we're looking at. I've removed the wedges, and instead of looking at a nice shiny black surface like in this slot, you see the semiconductive armor has just disappeared. This is the case, this is on a hydro generator, where the interface between the semicon and the slot and the stress relief coatings that cover the M winding, where they were not, that interface was not properly made, or the materials were not properly applied, and we get some discharges here. Very slow failure mechanisms. In fact, rarely will they cause failure directly. They just normally cause issues if you have ozone, and then ozone causes water leaks in your heat exchangers, or causes your bearings to fail, or retaining rings to blow apart. And all of those are real experiences that people have had. The PD itself hardly ever caused failure. Here's a case where the manufacturer kind of forgot to put the epoxy in. So this is the copper conductors, the insulation here, and you see voids that are in there. Still took many years for this to cause failure. And here's a case where now we're looking at the end winding area. Remember the area outside the stator core? You see the stator core here. And you see this manufacturer used big spaces here and little spaces here. And it turns out this happened to be a phase A line end coil, a phase B line end coil, and there was a lot of electric stress across this very narrow gap. It should have been much wider. We got PD, and the PD gave rise to nitric acid and created that white powder. But these are all very slow failure processes, usually taking many years, if not decades, to cause failure. Okay, and hopefully you won't be having those on your particular machines. However, there's always problems caused by aging. Just like as I get older, I get more wrinkly, I become more frail, probably my voice is not as good as it used to be. And the main failure processes are loose coils in the slot. This is a coil that's been removed from a slot, and you can see where this white area is where the insulation has been abraded away. The dark area, the black area here, is where there's the original semicon. That would be at the ventilation ducts in the core. But that's coil vibration. This is caused by the 100 Hertz magnetic forces in the windings, and windings not being installed tight in the slot or becoming loose over time. This is a coil that I removed from a motor that had seen about 20 years in service, and essentially I'm just looking at the side of the coil. Here's the copper. I peeled away the insulation, and essentially this is a thermal aging problem. If you operate a motor, for example, for 20 years with an RTD temperature of 120 degrees, 115 degrees, the epoxy essentially will gradually evaporate. This creates voids within the insulation, and we get PD. Forgot to mention here that once the semicon coating has been eroded away here, then that will create PD. And this is another winding. It was in a mining machine, mining motor. And what you see here is coils just out of in the M winding. Here's some blocking between coils, and we've cleaned away all the dirt and crap that was over the M winding, and underneath you see this electrical tracking. So contamination of the winding eventually will lead to a process called electrical tracking, which creates carbonized tracks over the surfaces of the coils or between the coils, and eventually will cause failure. So these are aging related issues. How quickly the machine fails depends on how conductive is that pollution, how high is the operating temperature, how loose is the coils. The PD itself is just purely a symptom, okay? Okay, so online PD detection. I've talked about what PD is. I've given you a little bit of an idea about what failure processes it's a cause or symptom of. In fact, this has been known for a long, long time that operating generators will produce PD. Virtually every machine 6 kV and above has it. In fact, almost every machine 3.3 kV and above has it to some degree. But the first reference to it that I've seen for online detection was a paper that was published in 1951 by John Johnson of Westinghouse, and he needed it to find the loose coils in the slot problem. And I was privileged enough to meet Johnny. I was a very young engineer. He was quite an old engineer. And so he gave me the lowdown on the whole history of what led to the test. In his very early tests, he actually used a RF, or that's a radio frequency current transformer, a high frequency current transformer at the neutral. And that's still the sensor that many people will use for EMI testing. But in fact, very shortly after that, both Westinghouse and GE, and back then it was Siemens and Brown Boveri and the Japanese manufacturers started to put the PD sensors, instead of using an RFCT at the neutral, where the signal is about 100 times smaller than it would be where the PD actually is occurring, which is at the high voltage, on the high voltage coils, they started installing high voltage capacitors on the machine terminals. And what the purpose of the capacitor is, a capacitor, for those with electrical background, you remember the impedance of capacitor is 1 over 2 pi FC, where F is the frequency of the AC, and C is the capacitance. And so if you use a capacitor and you have 50 hertz high voltage, and if you have a capacitor anywhere between 80 to a few nanofarads, what will happen is that capacitor will block that high voltage. It'll be a high impedance on the order of megohms or hundreds of megohms, and it'll block the high voltage. But because you remember I told you about those PD pulses, and they've only got a duration of a few nanoseconds. If you think about that as a half of a sine wave, you'll see every PD pulse in air creates signals up to the 200-300 megahertz region. In hydrogen-cooled machines, it goes up to well over a gigahertz, over 1,000 megahertz, okay, because of the pulses are even shorter in hydrogen. And so the idea is this is a high frequency signal, and at high frequencies, F is 1,000,000 times higher, for example, than at 50 hertz, and therefore the impedance of that capacitor is much, much lower. So it's a short circuit to the PD signals, but it's an open circuit to the voltage. And the reason why people started moving to capacitors installed on the high voltage terminals on the output leads is because it allowed us to see the pulses on each phase, so we could distinguish which phase the discharge activity was happening on. And as we'll talk about a little bit later, there's something called phase resolved PD, or partial discharge patterns or plots, how we look at PD with respect to the 50 hertz AC cycle. And these PRPD plots are much easier to understand if you're just looking at one phase at a time, rather than 3 phases where they're all signals from all 3 phases are joined together. Okay, so just a second, I have to cough. Hopefully I'm back. So online PD testing goes back to the 1950s. It was widely available as a service from most of the world's major OEMs, and the tests worked perfectly well. But it turned out it was the test, because it was online, you're connected to the power system, there's a lot of noise, electrical arcing and sparking occurring. Okay, and these are some of the sources of those things: electrostatic precipitators, slip ring arcing and sparking, variable speed drives, the switching noise from there, power tool operation, arc welding, any porous electrical connections in the plant will give off little arcs and sparks, which for the most part are normal and harmless within reason. Okay, and if you're measuring those, because you're connected to the power system and your capacitor is measuring those signals at the same time, it's also looking at the stator PD. And quite often, especially in the larger gas turbine plants, combined cycle plants, coal-fired and nuclear plants, that noise can be so high, that electrical interference can be so high that it really washes out the stator PD, and you need a really good expert to separate the PD from the noise. And of course, the original test service providers from the OEMs back in the 50s and 60s and 70s, and even now, had those kinds of experts. Okay, now let's hit that and then go down. I'm sorry, it's frozen on me again. Remind me not to cough next time. Good. Okay, so here is a phase resolved Prpd plots, and I don't have time to go into them a lot of times, but those of you who've been involved in measuring PD know we like to put the display the PD with respect to the 50 Hertz AC cycle. So this horizontal thing scale is the AC cycle from 0 to 360 degrees. The vertical scale is the PD magnitude, which could be in millivolts or picocoulombs or nanocoulombs or milliamps or dB or whatever measurement unit you want. Okay, in this case, it's between 0 and 150 millivolts and 0 and to minus 150 millivolts. And this is on a real operating machine, and this is very characteristic of what the PD pattern would be ideally would look like if there was no interference. Okay, in fact, this could have been one of the experiments I did when I was still in a university studying partial discharges. But this one's labeled, by the way, machine PD, but through mechanisms I'll talk briefly about in a few minutes, we can also separate the PD from the noise. And this is the noise, okay? And so if you have appropriate techniques, and there's lots of them out there, what'll happen is you can separate out the noise. In the past, and in fact, many of the systems that are still used by many of the, especially the OEM service providers, what they do is those two graphs are combined. But if you have some ways of digitally separating PD, stator PD pulses from the noise, you can isolate one from the other. And of course, once you've gotten rid of the noise or separated it out, then it takes much less expertise to look at this pattern and decide, do I have a problem with my machine? And is it thermal deterioration or is it loose windings? Okay, so these are the Prpd plots we always talk about, and so that's that noise that we have to somehow get rid of. And as I said, in the early days, a lot of expertise was needed, and a lot of the experts, so-called experts, weren't really experts. They were given a measurement technology and a few went on a few trips, and then all of a sudden we're out there doing tests with relatively little experience, and they came up with lots of false indications. Okay, what we call false positives. There was also false negatives, and we'll talk about that later. But there were false positives because they were actually measuring the noise. The noise was dominating the PD, and they thought the stator winding was in trouble when in fact it was noise. They would run to the plant manager and say, hey, we've got to shut this machine down. There's high PD, blah, 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 it might fail. Although in all my career, and I've looked at data from literally tens of thousands of machines and hundreds of thousands of tests, I've never said shut a machine down based on PD. At least not immediately. And the thing is, the plant manager then thinks they've got a problem. If they open up the machine and they find out there's nothing wrong, there's a credibility issue. That's called a false positive. And in fact, this was so widespread from all the different technologies and vendors that were out there in the 1980s that EPRI, now I'm not sure if you're familiar, it's a US organization, but I think ESCOM has been involved with them in the past as the Electric Power Research Institute based in the US, but one of their guys just said, hey, this PD monitoring is witchcraft, okay? It depended on the spooky spidey senses of a few knowledgeable people, okay? And it really limited the applicability of the machines way back then. And in fact, it led to utility-sponsored research to come up with a technology that end users could interpret without having to need all those gurus, okay? So to improve the credibility, we needed better noise separation techniques. And there has been lots of progress in this. And I don't have time to go through all of these. I encourage you to see these, look at these IEEE and IEC standards. IEEE 1434 is both for online and offline testing of rotating machines. IEC 6034-27-2 is for online testing of rotating machines. And IEC 62478, it is the standard that talks about all sorts of different kinds of equipment, and it's a companion to what some of you might be familiar with is IEC 60270, which is for low frequency measurements. This is for measurements above that low frequency range. And basically what you see if you read this standard and look at these standards, you'll find that there's been a lot of interest in moving to what was called the VHF or UHF frequency ranges for PD detection. I'll get into this a bit more later, but a very high frequency, that's frequencies really 30 megahertz to 300 megahertz. UHF is 300 megahertz to 3 gigahertz. Moving to much higher frequencies of PD detection than the traditional techniques that were around, which were typically around 1 megahertz. And in fact, this move in rotating machines to this high frequency range has been exactly duplicated in transformers and GIS, where you want to measure the PD on power transformers and GIS. It turns out if you're moving and measuring in those higher frequencies, you're going to be much less sensitive to arcing and sparking outside of the test object, the transformer or the machine. Okay, and this standard here goes into a lot of detail on that. And as I said, for rotating machines, these standards talk about this. With the move to VHF and UHF techniques, we're also able to introduce the time of flight measurement, and I'll explain that a little bit later to separate PD. We also can distinguish PD from noise based on the shape of the pulse. Now that can be done in hardware. That's my preferred route. That's the technique I started using in the 1990s. Or it could be done in the low frequency range using something called time frequency maps, which are popular, although there are some assumptions involved in that. So there's hardware and software ways of looking at the shape of the pulse, because it turns out PD within a stator winding tends to have a different shape of pulse than most kinds of noise, okay? So I don't have time to go through all of these in any great detail, but to measure the PD, just like if you're doing an offline test, you need that sensor. I said we could put a sensor at the neutral, an RFCT, for example, but by far the most common way of detecting PD is to put a single capacitor or 1 or 2 sensors per phase on each phase of the motor or generator at the machine terminals, at the high voltage terminals, because you'll be much closer to the PD signals. You'll get less loss of signal at that particular location. And by far the most common sensor is the 80 picofarad capacitor. Just ourselves, we've installed, I think it's close to 80,000 of these capacitors now around the world on 18,000 machines. Okay, and they measure in the VHF frequency range. And you can see these kinds of capacitors here connected to the terminals of a small generator. Okay, the next most common is measuring in the low frequency range. So that's less than 1 megahertz formally by IEC 60270, or more. For most vendors of low frequency test gear, it's less than 3 megahertz. And there you can use a larger capacitor. The ones we supply are 1 nanofarads, but others supply capacitances up to 10 nanofarads. Again, remember, these capacitors block the AC voltage but allow the PD signals to come through. Okay, so here we're starting to talk about the low frequency versus very high frequency dichotomy that's happened, but it's crystal clear that the end users have gone primarily for the VHF methods. Okay, for hydrogen-cooled machines are more difficult for us. There's a lot of auxiliary equipment in coal-fired, nuclear-fired units, the very large combined cycle plants. So the noise environment tends to be much worse. And it turns out high-pressure hydrogen makes the PD pulses much lower. Okay, and that's a whole nother separate topic. But in fact, what's happened is that the most popular sensor for hydrogen-cooled machines is something called the stator slot coupler, or SSC. You can see one of those installed in a turbine generator. Number of limitations with this SSC technique, because it can only be installed during a major outage where the rotor is pulled, and it's only sensitive to PD in that slot, where 10 capacitive sensors can be sensitive to more broadly throughout the winding. Okay, but if you are using capacitive sensors, the IEEE and IEC have very strong guidance on tests that the vendors of those sensors must do to make sure that those capacitors don't fail in service. Because if you have a PD sensor on a high voltage terminal and it fails, if the capacitor or the PD sensor itself fails, you're going to trip that motor and generator. And plant managers, they have no sense of humor when a condition monitoring system causes the trip out of a generator or a motor. Okay, so because of their critical location, these standards have lengthy discussions and annexes of what you must do or end users must do to make sure the sensors themselves do not lead to failure. Okay, so we've talked about sensors, let's just talk about, I'm gonna specifically talk about a Vhf technique where we use 80 picofarad sensors, 2 per phase. And essentially all as we're doing is we're recognizing it takes time for electricity to travel. Now this would be the motor generator. Normally it's going to be a generator. Okay, and there's variations for hydro generators, but what we can do is install one sensor right at the machine terminals and another one some distance away, maybe 5 meters or 3 meters away from each other. And remember, electrical pulses take time to travel. There is something called the speed of light. The speed of electricity in air is 3 times 10 to the 8th meters per second, or 0.3 meters per nanosecond. So it takes time for a pulse to travel. Remember those PD pulses I showed you? That's why I showed you those pulses a while ago. Those pulses are very, very brief. They're only lasting a few nanoseconds. So we know precisely when they occur. And so if I have a PD pulse coming from this direction, it's first going to be detected by this sensor. And then if, say, this is 5 meters here, it's going to take 15 nanoseconds for that pulse to reach this sensor. And if we have an appropriate electronic box in hardware, we can see that the M or machine input goes high, digital high, 15 nanoseconds before the S or system sensor goes high. And so we can say, hey, if that happens 15 nanoseconds apart, especially if we know that delay time, which is easily measured when you install the sensors, then you can separate that PD from the power system or from the machine. Whereas if we have corona PD occurring on a whole high voltage transmission line, it couples through the transformer and then comes in to the output bus, in this case an isolated phase output bus, it will be traveling from this direction. And of course that pulse will arrive at the system sensor input 15 nanoseconds before it reaches the M input. So S goes digitally high before M goes high. And we have an electronic decoder that says, hey, that pulse, if that took 15 nanoseconds, that was 15 nanoseconds delay, that pulse must have come from the system. And of course, if we have any arcing and sparking, broken insulators or poor electrical contacts, the flexible links on your isolated phase bus or your output bus, they are going to get there less than 15 nanoseconds apart. So we can tell whether pulses are coming from the power system, from the machine, or from between the sensors, okay? And this actually gets rid of quite a lot of noise in many practical situations, okay? And in fact, you can see this in this plot. This is a standard plot that we can print out to see, hey, in this case, so this is the phase resolved. This is in my case, that was probably 60 hertz. This is a measurement done just a few weeks ago that I happened to come across in reviewing a report. And so this is from the machine. This is between the two sensors. And this is activity occurring from the power system itself. And we see very clearly, look at this vertical scale, 30,000 millivolts, 30 volts. Normal PD on a hydrogen-cooled machine, I'm going to tell you, it's normally 30 or 40 millivolts. So this is a signal, 1,000 times bigger, okay, is occurring. And it's occurring, it turns out, between the sensors, and we can isolate it from here and here. We can then just expand this scale and see where the real PD is. But what's happening here is we've been able to isolate it between the sensors. And in fact, this is a very characteristic plot for a broken ceramic post insulator, okay, what we call a gap discharge. Okay, so we can help locate the things, but the main purpose is to allow us to isolate the PD from the stator winding from things coming in from the power system. Now, there are other ways of doing it. There's the pulse shape analysis technology. There's various digital ways of using post-processing where you implement pulse shape analysis, but afterwards they call it time frequency maps and clustering. But there are these different techniques that can be used. Okay, so now what I'd like to talk about is a little bit of interpretation, not only how are we doing that interpretation these days, but some of the limitations of that interpretation, okay? Because when you have stuff installed in 18,000 machines, you'll learn a thing or two, especially when you're someone like me who's used to crawling around windings and finding what the real issues are. It's still the best way of determining the condition of the winding is to do a really careful visual inspection by someone who's been doing that for most of their career, okay? Not some management person. Okay, so interpretation, one of the ways we try to interpret, well, you know, do we have a problem or not, is by have we got tables or lists or guidance on what is high PD, okay? And this is just like with bearing vibration monitoring. If the bearing vibration is above certain limits in displacement or acceleration or whatever, for specific types of bearings, we know, oh, if the vibration level is high enough, that bearing itself is probably going to start self-destructing and then cause a failure. So we've just like bearing vibration, we've established what's really high levels or low levels. We've been able to do the same thing for the most part in interpretation of PD levels. And of course, the purpose here is identifying if you have 100 machines, which 3 or 4 machines do you really need to concentrate your maintenance activity on? And so you can ignore, take fewer outages or less testing of the good machines. Okay, so high PD, in the beginning, if you read some of my papers in the 1980s and early 1990s, I didn't think we could ever actually determine whether a machine was good or bad based on vibration. That was based on the theoretical knowledge of how PD manifests, it gets from the stator coil to the machine terminals. But the idea is eventually we were doing enough analysis, and I have a colleague of mine, Vicki Warren, who still every 2 years does an analysis of our database, and I'll show an extract of that in a few seconds. That we have, and comparing those levels that we find on a wide number of machines with the actual condition of the winding as determined by a visual inspection by someone who's knowledgeable at looking at stator windings, we have been able to establish what levels are high, okay? And it turns out it depends on the rated voltage, it depends on the pressure if it's a hydrogen cooled machine. Oddly enough, it doesn't seem to depend on the megawatt rating, whether it's a 1 megawatt rating machine or a 100 megawatt machine. As long as the voltage rating is the same and it's operating in air, we seem to get the same statistical distributions of PD. And these tables, which we've only been able to determine for the VHF and UHF detection methods, but these have been independently third-party validated. Some of you might know Clyde Mon, a nice old gentleman, 94 years old now, who many years ago looked into our database, looked at the evidence, and independently validated. Other utilities have validated the databases. So we have been able to establish what we call alert levels. I try not to call it alarm levels, it's alert levels, because remember, just because you got high PD, it doesn't mean the machine's going to fail right now, okay? Something that I think I'm going to address a little bit later, but these limits, although our guidance that I'll show you in the next page are show limits that encompass all failure processes within the stator winding. In reality, I know that's not true. I need separate limits for different insulation aging mechanisms. For example, if I have PD occurring right next to the turn insulation in a motor which has multi-turn coils or a small hydro generator with multi-turn coils, and I have PD within that ground wall, right in the stack, right in voids, right between the turn insulation and the ground insulation, that can actually produce relatively low levels of PD and can cause failure much quicker than PD signals from, you remember that white band I showed you on that hydro generator where the semicon had been disconnected, electrically disconnected from the stress relief coating or the grading coating or the ECP. That sticks into the M winding because of manufacturing issues. So when I got that thing, that produces exceptionally high levels of PD, okay? But in fact, it might not lead to failure anytime soon, if ever. Okay, so this is one of the things we're working on, is to try and come up with databases or alert levels that depend, that are focused on each of the failure processes, but it's going to take a lot more data that we've got now. Okay, I also need to point out for the low frequency detection system, whether it's ours or others, I have seen no third-party validated tables for what are high levels of PD. I know there's lots of vendors who give out numbers, but they're suspicious right off the bat because they don't depend on hydrogen pressure, they don't depend on voltage, they don't even really depend on the sensor they use, it seems sometimes. So they're a little suspicious from that point of view, but in fact, other people have not been able to independently validate those levels. And there's good, strong reasons for that. I encourage you to read the IEC and IEEE standards I talked about before, okay? Fortunately for us, when we measure in the VHF and UHF range, stator windings are not inductive capacitive networks. They are in fact surge impedances of a fairly narrow range from a 1 megawatt machine to a 2000 MVA machine. The range in impedances at those frequencies, surge impedances of those frequencies, is very narrow. And that's what has allowed us to create scientifically based and validated high alert or high PD levels. So this is an example. As I said, this data is only from portable or periodic testing of the machines on, in this case, 7,000 machines. We have about 18,000 machines equipped with sensors of this sort, okay? But only about 1/3 of our customers actually give us the data. Most of them hold on to it. For example, I haven't seen any data from ESCOM or SASOL in the last several years. So that can't be incorporated into our database. But based on those 680,000 test results on about 7,000 machines, we've been able to create statistical distributions of the PD, and we found that if your PD on your type of machine is higher than 90% of other similar machines, that means voltage rating and hydrogen pressure, that typically if we open up the machine, we will see a significant insulation problem. But you see it depends on the voltage class, and this is just an extract of that. So for example, if I have 11 kV machine and 400 millivolts, if the PD is higher than millivolts, and this is something called Qmax, which is defined in the standards, then we have some concern, okay? That would be your trigger point for starting to monitor that machine a little bit more carefully. So these are the levels. So it's like high vibration levels. These define the levels. Unfortunately, they're only valid for the VHF and UHF technologies. Okay, of course, the other way of detecting PD is to measure the trend in PD over time. And this is valid for all technologies. It doesn't matter what you're doing, whether it's low frequency, very high frequency, or ultra high frequency PD detection methods. And essentially, as long as you're measuring the PD itself and the experts have, or the hardware or the software has separated the PD from noise, you're just looking at the stator PD itself, we know no matter what technology you're using, if it's doubling, if it's increasing by 100% every 6 months to a year, then that is a significant rate of increase. So this is Qmax again, QM, as defined in IEEE and IEC standards. This is an old case study from the utility I used to work from, 1988 to 1996, where this was a hydrogen cooled machine. Turns out it had relatively low levels. Think of that machine before, and then the PD started increasing, and over a 2 or 3 year period, basically increased 10 times in magnitude, 1,000%. And eventually we convinced the plant manager, the asset manager, they really need to take an outage. We were pretty convinced it was loose windings in the slot. There was also lots of oil leaking into the machine that loosened the coils in the slot. And of course, we got it early enough so we were able to re-wedge that machine, clean up the oil as best as we could. You never really can, and it came right down. Most times, though, maintenance will only level things off, okay? But the trend is not always perfect. It does not always work, okay? So again, this is something I published, I guess, 10 or 12 years ago, where kind of it's a cartoon which basically looks at the peak PD magnitude versus the years. We see the PD, and this caused me a lot of grief in the beginning. I gave a lot of grief to some manufacturers that their new windings were better than their old windings, or rather their new windings were worse than their old windings. And you see the PD tends to go down in the first 6 months, year or so, depending on how much you're operating that machine during that period. And then hopefully for decades, it'll be flat. It won't be flat like this. It'll be going up and down at least plus or minus 25%. Okay, and this trend, by the way, would only be valid under the same load conditions and same voltage and all that. There's a lot of issues with trending over time, which is why continuous monitoring's become more popular. But then, hey, the oil leaks into the machine, the windings get loose, they start vibrating in the slot, grinding away the insulation, getting lots of slot discharge, but it doesn't continue increasing until it fails. Unfortunately, we've learned, and we've had many false negatives because of this, where we thought a machine was good, but in fact it wasn't, especially in the days before we had our alert levels. And it turns out there's various physical mechanisms or theories I propose that the PD, but it's something we actually do find, that the PD just stabilizes. It doesn't continue to go up. In fact, sometimes it even goes down. Okay, so if I installed sensors, and many people want to install sensors on older machines, and I really want to see it here so I can see this transition region. But if you install sensors here, and especially with low frequency detectors, you don't know what's high or low, then you might think that machine's perfectly good, when in fact it's still continuing to deteriorate and it will fail. So that's a limitation. This is what I advertised earlier. I want to talk about the things it can do, but also the things it can't do. Okay, there's some other issues with online PD monitoring. Okay, there's almost a new supplier almost every month, especially out of the Asian region. Okay, and they put a few sensors in, they collect a few results, and they claim, hey, this is perfect. This is the newest, latest technology. This works, and it'll find all your stator winding problems. Okay. It's not true. One, PD can't find all stator insulation problems. I already talked about that. It won't find turn-to-turn issues. It won't find unwinding vibration issues until you're further along. An online test will never find problems at the neutral, okay? Unless you want to put a sensor at the neutral, okay? So there's limitations of what PD can do. I still think in air-cooled machines, it finds 80 to 90% of issues. Okay, hydrogen cooled machines, it's really good for finding loose coils and contamination of the M winding. I don't normally see in hydrogen cooled, direct water cooled thermal aging as a failure mechanism. Okay, and so this is an issue. The stator wind PD can find many important failure mechanisms, but it will not find everything. If you have a new test, as I mentioned before, you really need a lot of third-party validation to make sure it actually works if you're investigating a new technology. It's just too easy for people to say, oh, I've got this great new thing. They tried it on a few machines and there it is. Okay. Many people now, especially because it's easy to do post-processing and data manipulation afterwards, and many people, because of that, are saying, hey, we can detect all or separate out all noise. And that's not true. Okay, there are still false positives, even if with us, and I didn't get into it in detail, but we use 4 independent ways of separating PD from noise. Our false indication rate when we started at Iris was about 15%. Okay, it's now down, and has been for the last several years, about 1.5%. So we have a false positive rate of about 1.5%. And maybe that sounds good, maybe it sounds bad, but I can tell you it's bad, because when you monitor 18,000 machines, and we're talking about maybe 1,000 of those machines are going to have insulation issues, and then you can do the math. 1.5% of those 1,000 means still a lot of emails to me each year for, hey, how come you said there was a problem when there wasn't? There's also false negatives. Okay, so when people are proposing new methods, new technology and stuff, make sure it's gone out and been validated first. You don't want to be the guinea pig, okay? And it should be not validated by independent third parties. And I was fortunate enough when we developed the techniques that I'm involved with in the VHF and UHF way, it was funded by the utilities well before it was ever, all that research was funded. It was a $2 million R&D project, well before before there was any commercial license or manufacturing of the thing. And those utilities then made sure the techniques would work independently and validated what they found via other means. Okay. Another problem with PD monitoring is some people claim it can predict remaining life, and there's all sorts of folks leaping around out there saying they can predict the remaining life of a winding. And I know asset managers and plant managers want to do this because they want to maximize the investment they've made in the current machine or the current stator winding. Okay, and unfortunately, there are a number of organizations, they're usually service organizations, who will go around claiming they can do that. And personally, I don't believe it. Certainly not using PD alone, and not even using any of the other diagnostic tests. EPRI has spent a lot of money trying to validate those things in the past, and under third-party validation, it just hasn't stood up. Okay, so make sure if people are claiming remaining life and all that kind of stuff, that has been independently validated in blind testing, where the vendor was not involved. Okay, and to my knowledge, I know of nothing that allows us to predict remaining life, and I know I want to, but I don't think it's possible yet. Maybe not ever, at least not with electrical measurements on stator windings. Okay. Other problems with PD monitoring is what is high PD. I think I've kind of addressed this a lot. It turns out in the low frequency measuring techniques, because at low frequencies, the stator windings have all sorts of capacitance and inductances. It's a very complex inductive capacitive network, lots of natural frequencies or resonance points. It's been very hard to establish what is high PD in the lower frequency range, especially those people have a tendency for complete windings to use picocoulombs or nanocoulombs, including ourselves with our Delta Max. That's the measurement unit that comes out. But if you read the standards, it's crystal clear that we can't use charge. Okay, soon as you introduce inductance into the capacitive network, you're going to have natural frequencies, resonances, and stuff where you'll get completely different readings. And there's papers out there, certainly some I've done and other academics have done, that show that you'll get, if you use brand A on the same machine and brand B on the same machine and brand C on the same machine, all more or less at the same time, you can get a 30-to-1 difference if you're using picocoulombs or nanocoulombs. So the point is not that you can't use those, but remember, it can only be used for comparative basis, or when you're comparing that exact same low frequency test equipment in the same frequency range on exactly the same kind of machine. Okay, so it's easier for OEMs to use those kinds of measurements, but it is purely comparative. It has really nothing to do with the size of the spark that's within that winding. Okay, and we can get back to that a little bit later if you want. Okay. So, in conclusion there, we still need better ways of determining which machines need maintenance, okay, which is the whole point of looking at the trend and the magnitude. Okay, one of the other nice things about online or any kind of PD measurement on any type of apparatus, that it can sometimes indicate the nature of the PD. Where is it occurring? Near the copper, near the core. It can sometimes, by looking at what we call the phase resolved PD patterns that I showed you earlier, it can sometimes help us identify that there's certain characteristic shapes that are associated with certain magnitudes, looking at the relationship between positive and negative pulses, where they're occurring with respect to the AC cycle. And these things can sometimes help us identify the mechanisms, especially in other assets like transformers or GIS and cables, okay, where there's relatively very few PD sources and usually only one or two acting at any one time. Unfortunately, in machines, we have many different kinds of PD sources that can occur. Each one of those mechanisms I pointed out before can have quite a distinctive PRPD pattern, and they all behave differently as you change the voltage or load or temperature, this winding temperature, or the load in the winding, or the humidity. Each mechanism will behave a little bit differently. And so we can use the PRPD plus the effective operating conditions on the PD to help us identify what the root cause is. But because we have so many different sources of PD, not just a few sources, but 1,000 sources in a typical winding, each creating their own little PD pattern, it's turned out to be actually really difficult. And I know people have come up with all sorts of transformation methods and all that kind of stuff, and all sorts of technologies and stuff to help us identify different processes or separate them out. But the reality is, even if we just use the PRPD plots by themselves, even in an ideal situation of, say, loose coils in the slot, unfortunately, reality is what's going to operate here. When you go in and look at the machine, do the visual inspection, you're going to see these windings are vibrating in their slot discharges on the surface of the coils. And 20% of the time, this is our experience, 20% of the time that PRPD pattern is not correct. It doesn't necessarily always show a positive predominance. Okay, it might not always be in the part of the AC cycle where you expect it. It might not have that nice special triangle pattern that we often associate with PRPD patterns. And again, we've learned this the hard way because we've given false information or incorrect information to customers sometimes, just purely looking at those PRPD patterns, and we've found that they're sometimes wrong. So don't go overboard with those things. And I know I'm probably the most guilty guy. I published the first patterns way back in the 80s for using this kinds of technology, using research tools. But I'm sorry, I was wrong. I'm guilty of the same thing I accuse others of, that they've overclaimed. But reality is what intervenes, and it's the condition of the winding that's determined by visual inspection. That's the most important way of identifying the root cause. And of course, if you predict the wrong mechanism based on PRPD, then what will happen is you might do the wrong repairs, or you're prepared for the wrong repairs when you do take your shutdown or your outage. Okay, and so it causes real harm to the end user. Okay. Another issue we've got is false negatives, okay? So kind of don't like talking about them. Again, I get about 5 or 6 per year on average. They've settled down a little bit. And if anyone's ever looked at our install guides, you'll see it's expanded from about 5 to 6 pages to 80 pages, because most of our false negative indications, that's where we say a machine's good, but in fact it fails, or we open it up and find severe issues. That's a false negative. It's a real downer. Okay, we don't really like false negatives, and we try to do everything. And most of those false negatives have been caused by inappropriate sensor installation techniques. And I know that's happened sometimes in certainly at least in ESCOM, possibly also in SASL, where data we thought the machine was good when it really wasn't. Here's an actual real example. In fact, I was supposed to publish a paper at an IEEE, or present a paper at an IEEE conference in September. Unfortunately, it's been delayed, where I showed a whole catalog of false indications. The sales guys at Iris, they hate me because I go around talking about all the things we can't do. And but I just want to be straight open, and I'm an old enough man, I don't really care about any of the commercial aspects anymore. But this was a relatively small turbine generator, or 85 megawatt machine. And this is the first thing I knew about it. They sent me this picture, and this machine had clear loose coils in the slot, probably for a long time. They had oil in the slot, and it had classic slot discharge failure in the line end coils, okay? It turns out literally just a year before this failure occurred, they had installed our Vhf PD monitoring system, the 80 puff stuff, so we should be able to interpret the magnitudes. We didn't have a trend established, but we should be able to interpret the magnitudes, and we can see the PD is only getting up to 30, 40, 50 millivolts, okay? And if you remember that table a little while ago, I think this was 11 kV machine, you know, we're looking for 300 or 400 millivolts. And here's this only 50 millivolts. We said, don't worry, be happy. And then the machine failed, okay? So this is a false negative. They happen. Okay, we do everything we can. Every false negative I hear about, I investigate personally, because it's the only way we can improve the technology. And a lot of that has resulted in improved ways of installing sensors and being a little bit more careful about what we can detect and what we can't detect. Why I think the PD was, and this is a theory, why we did not detect this PD, because it was very severely deteriorated. This is actually where it failed, but if you saw the rest of the coil, I got on a plane and flew, well, to India. It was in India. Flew over there as fast as I could to find out and understand what was going on here. And I saw all the other coils. They were all severely abraded, okay? What I think happened here, there was a lot of oil, there was a lot of debris in the slot. And I think what really happened is that oil mixing with the debris in the slot actually kind of made a partly conductive goo that reestablished the semicon. Okay, and therefore suppress the PD, even though the bar vibration, which was driving the failure mechanism, was still occurring. Okay, so this is something here that that's just a theory. I have other theories for when machines are very thermally aged. We sometimes see the PD levels off and goes down, and we've had false negatives because of that. If you get a chance to see this IEEE petrochemical industry conference paper, unfortunately, it's not going to be presented for a year now. There'll be several other examples and theories about why we might have had a false negative. Okay, so that's the bad news. Let's move forward. What have we been working on lately? Of course, we've been looking at better sophisticated ways of identifying the different failure processes using Prpd. Some of you might remember an old program that we called MICA, the Machine Installation Condition Assessment Advisor, which ESCOM for a short time was using. But it was a true expert system to analyze the plots plus other data to try and give a condition assessment that even a non-rotating machine expert could use. Okay. Since then, the technology's advanced. There's lots of artificial intelligence methods out there, and we know we're not going to be the experts at AI, okay, and neural networks and all this other kind of stuff. Various other kinds of pattern recognition techniques. What instead we do, many of these are created by academic universities, and I love evaluating them, okay? But we've had some problems because all of these techniques that we've evaluated, maybe half a dozen, two-thirds, maybe 6 or 7 of these over time. I give a set of data that they can train their system on or give the typical examples of all that, and everything's hunky-dory, 99% perfection in identifying things once they tweak all the variables that you can do with these AI systems. Unfortunately, though, then I send them another set of data, unfortunately, where I don't give them the answers, okay? And then life is not good, okay? You have a better chance of getting it right, okay, by flipping a coin, okay? So I've become a little bit cynical about this. It's kind of like self-driving cars. Remember, we're all supposed to be able to drive self-driving cars now, and now they're saying another 20 or 30 years, maybe, okay? But the AI technology has been overhyped. There's lots of articles out there on this now, and the application to Prpd is one of those places. But we're still interested in learning, because one day someone's going to come up with a system, and then hopefully I can use it. But remember, all of them fundamentally use the Prpd patterns, and unfortunately those patterns themselves sometimes are wrong. Okay, the other thing we've been working on is on continuous monitoring. We've been dabbling in it since 1994. Now we're up to 5,500 machines, motors, and generators monitored with continuous monitoring. The primary reason people are doing it is because you get much better trends. PD is affected by load, temperature, etc., voltage, humidity for surface PD mechanisms, and you'll get a much better trend with continuous monitor, where it's a simple filtering mechanism to filter out all the data that's not in a very narrow band. Okay, so that's what's been driving it. The other thing is, I'm not sure if it's happening in Southern Africa yet, but certainly in Europe and North America, a lot of big utilities, a lot of big industrial companies are putting in centralized condition monitoring centers. These are not control centers where they measure the voltage and the currents and have alarms and trips and stuff. These are for the maintenance engineers, where you have a centralized system. And so the continuous monitors just feed right into whatever intranet within the company intranet, because there's also cyber security issues involved. And so continuous monitors go on there. We're now in our third generation of systems. Reliability of the components, especially in very high levels of temperatures and humidities, has been a big issue. Okay. The other thing we've been moving towards is integrating stator PD with other types of rotor and stator monitoring systems. So some of you might be familiar with, not only do we do stator PD, we're not a PD monitoring company, we're a winding monitoring company. So we also do unwinding vibration, flux monitoring to detect problems with shorted turns and aging of the rotor insulation, shaft voltage and current, shaft ground monitoring, both of the voltages and the currents. And we've integrated all of these into a single platform. So you have a common hardware platform that fits inside here, and a simple, or maybe not simple, but a single software platform. In the past, we would sell 4 different monitors, and you'd have to learn how to use each one separately. We've spent a lot of effort to bring this all together into a common hardware and software platform. Okay, so that's where we're moving. Still trying to automate Prpd recognition, and a big move to continuous monitoring, because it makes trending better, and it facilitates those centralized condition monitoring sensors that many people are installing these days. Okay, I'm pretty well close to the finish. I just want to talk a little about low frequency versus very high frequency. I think when I've been in South Africa and doing seminars in past years, this has been a question that I've asked. I've actually given an actual separate IEEE paper on this a couple of years ago, and so you know, contact Neil or email me or whatever, and we'll try and I'll get you a copy of that paper. I can send them out as individual papers that address it. As I said, we're one of the few folks who make both low frequency system and VHF systems and sell it to the market. We don't really have a commercial bias there, but I can give you some certain things with the low frequency methods. Of course, they're really the original methods going back to the 1950s. They normally use capacitors in the range, as I said before, 1 to 10 nanofarads. Okay, and of course they work up to formally 1 megahertz according to IEC 60270, but in reality, most people have their hardware good enough to 3 megahertz. That means 10 megahertz digitization rate. And in contrast, the VHF is a bit more modern. It uses 80 picofarad sensors, and it works in this frequency range, the VHF frequency range. Okay. One of the things that is commonly said, and there's lots of discussion on this in IEEE and IEC standards for rotating machine PD monitoring, is that maybe the PD with low frequency, you're going to see deeper in the winding. And the basic fundamental theory is, if the stator winding looks like just a bunch of series inductors representing the coils between line and neutral, the impedance of a coil is 2 pi FL, where F is the frequency and L is the inductance. And if you have just simple inductors between line and neutral, if you have PD occurring deeper in the winding, it's got to go through more inductance to get to the machine terminals. And that's going to result in a higher reactive impedance, 2 pi FL, okay? And you're going to get some attenuation. If that attenuation is, if you measure at 1 megahertz, you're going to see it's going to be that attenuation is going to be less at 1 megahertz than it is at, say, 100 megahertz, which is where you'd be in the VHF. There'd be a higher frequency, therefore a higher impedance, so you're going to see less of the signal. The reality is actually a lot more complicated than that. There was a nice paper given at the IEEE Electrical Insulation Conference just a few weeks ago, given by a competitor, actually, but it actually showed that there's a big difference in attenuation based on frequencies, what frequency band you use in the low frequency range. On the VHF, actually, though, there was very little attenuation from neutral all the way up to the winding. And of course, myself and many academics found that out over 20 years ago in the 1980s when that work was being much more widely investigated. So there's a little bit of question still about that, but in the low frequency range, you have to be very careful about which frequency you use because you can get a lot of attenuation because it's not just a simple inductors. There's L's, there's a series inductance in the slot, series inductance in the M winding, capacitance between coils in the M winding, capacitance to ground. It's a very lots of mutual inductances. It's a very complex network, and there's lots of notch or filtering or resonances and anti-resonances going on. So the frequency is very important. Fortunately, when you get to the VHF, it behaves more like a transmission line. There is some attenuation, but it tends to be on the order of 20, 30, 40%, not the hundreds or 200s of percent that you might find in the low frequency region. Okay, because the low frequency region tends to have a lot more noise, you see a lot more noise from the connected power system, you need a lot more expertise, and I know there's been lots of development to try and automate that, but it's still really a fair amount of expertise even to use that clustering type software. And as I said before, there is no consensus on what's high or low PD. When we look at who buys the systems, the low frequency technology tends to be bought by the OEMs and the service shops who provide testing services. In the VHF, I guess, it's kind of just different, okay? It is easier to separate the PD from noise. That's recognized in all the standards, and most people will acknowledge that. And you allow then to use time of flight and pulse shape analysis to separate that noise. So there's a fairly low risk of noise. False indications, then we've driven it down to 1.5%. The severity tables of which high or low, unlike with low frequency where it depends entirely on the specific winding, the specific detector is connected to, and so you just can't get one number that says, oh, if you're above 10 nanocoulombs, you're in trouble. Okay, we have been able to do that in the VHF range, again, because of the impedance. It looks more like a surge impedance. And virtually all the people who buy the VHF system are the end users because they expect to be doing the interpretation themselves. In the interest of time, and to allow enough time for questions, assuming anyone's still listening, I'm not going to address the PD and EMI testing issues unless it comes up again in the thing. But it's just a comparison of both. I certainly was doing EMI monitoring, or I called it RF monitoring, back in the 70s and 80s. It was one of the major techniques we were using then. And of course, then you have various kinds of online PD. But when you see the presentation later, you can study that and always get back to me on that. Okay, so just in conclusion, online monitoring really started off as kind of a witchcraft thing, if I can use that word again, in the early 50s, where it was clear some people could get good, useful information to plan, to find out what the condition of the winding was without taking the machine out of service, and therefore plan your maintenance. But others had very poor experience, okay? And but this led the utility industry to come up with a technique that utilities themselves can use, so you weren't so dependent on an expert or a service organization that might have a bit of a conflict of interest. And it's clear now the VHF systems are very widely used in 18,000 machines around the world, virtually everywhere now. But it's been a 70-year transition, and there's still improvements that are coming in that technology. And with that, I'd like to conclude, but I'll leave this as a last slide up there. So just some references that for the most part, a couple of them I mentioned in the past, but there's other things, and some of them are books that you might find helpful. Okay, so that being said, I hope somebody is still there. Neil?
Yeah, Greg, I'm here. It's good. On that side, we have a couple of questions that have come up, and one that you did predict. I'll just start from the top and go on from there.
Okay.
What are your thoughts on using Rtds for PD detection?
I'm sorry. I actually did refer to that. That's a great question. I did refer to it in the slides, but I think I skipped over it, so I apologize for that. As far as I know, I was the one who first proposed and first did a lot of experiments for using Rtds as partial discharge sensors. Rtds, of course, are the resistance temperature detectors. They're primarily there in stator windings, and we're talking specifically about the slot Rtds. Okay, the Rtds, now there's a misconception. The Rtds themselves do not detect PD at all, okay? They're just too short and they've got too high a resistance for the microvolts and the millivolts to be induced in them. What actually detects with Rtds, what the sensing element is really the lead coming from the Rtd, which then goes through sometimes a little bit along that slot and then radially out or down to the end of the slot and then around the end windings. A lot of difference between motors and generators. So what actually detects PD in a stator winding when you're using Rtds is the leads coming out from it. And of course, that's only going to be valid if the leads are unshielded, okay? If you have shielded RTD leads, which about half the motor manufacturers at least and generator manufacturers tend to like shielding, putting a coaxial shield around the RTDs, you'll find very little signal there or none, okay? When I did my initial experiments, of course, at that time I was a young engineer. I thought the RTDs were going to be detecting PD in the actual slot where it says that PD is in, and very quickly realized that was not the case. When I actually looked at the machine and where's the RTD, found out that wasn't this, and that's of course what led me to the conclusion it's the RTDs, the leads that actually detect it. Okay, so, but in the initial research phase, this is when I had no conflicts of interest. I was just, you know, someone working for a utility trying to improve online PD, and RTDs were an obvious, or thermocouples, you can use thermocouples. They were an obvious way to do things. My problem is we also had this little requirement that says you got to reduce the false indication rate, okay? And that means suppress the noise. And it turned out with RTDs, you have a very low signal noise ratio. And with the company that's still involved in it, you know, they've gone through a number of company name changes, but one of their earlier researchers on it acknowledged that, in fact, when you're detecting it, it's wrong about 33% of the time, 1/3 of the time, because you're really picking up noise. It's preferentially sensitive to the noise because you're running right beside the stator core, and it's going up and down with high frequencies, as anyone who's ever done EMI monitoring would know. Okay, so given that limitation, we didn't pursue it in the research project before IRIS was established, because it was, the false indication rate was too high, and it didn't actually tell us where the PD was, because we didn't know in most cases where the RTD leads were running. And then Toshiba, Hitachi, and Mitsubishi, I think, some of the Japanese manufacturers saw an early reference to it in some of my papers back in the 1980s, and so they pursued with it, and I believe they've all stopped, presumably, I don't know why, but presumably for the same very high risk of false indications, okay? And I note that the company that's still out there, that's still the only company I think that's still pursuing it now, still really they've been good about it, and they put in print in a technical paper, an IEEE paper, that if you're going to use RTDs, you still have to install conventional sensors, either the RFCTs or the capacitors on the machine terminals, because the signal levels by themselves have almost no meaning. It depends on how long is the wire running close to the PD source. So I took a look again after some of the Japanese manufacturers to make sure things hadn't changed in the 2000s. And looked about it with more modern equipment and more sophisticated noise separation techniques, came up with the same thing, wrote a paper on it. So there's nothing wrong with measuring it using PD, measuring PD via RTDs. But be very careful. You better have a world-class expert looking at it, not somebody who just learned a few days ago or even a few years ago. Looking at the data, because how you decide whether it's really PD and not noise is still using the phase resolved PD patterns, and you really want them recorded with high resolution, okay? Secondly, you need to be aware that when it says, oh, it's in slot 23, well, it usually isn't in slot 23 if you actually go and look. Okay, there you'll find that's usually a low voltage coil, and in fact, what you'll see is the wires running against, maybe over the end of one of the cores and arcing and sparking, and then there's discharges occurring on the stress relief coatings just outside the slot, and it's picking that signal up. It's really like a coat hanger antenna. So with those limitations, does it provide any extra information? Well, in our continuous monitors, we provide all sorts of channels. So yes, you can hook them up if you want. I just don't know how to properly interpret them without misleading people, the end users, a lot with them. So knock yourself out, use them. But the reality is, even the people who are the only company now that I think is providing them or suggesting it has said very clearly, you still have to put in traditional sensors, okay? So there might be some follow-up on that, but sorry, I was supposed to address that earlier. Any other questions, Neil?
Yes, okay, we've got another one on SCCs. Why does SSCs only measure in the slot? If the PD current, let me just finish the whole little statement, then you can go. I'll start again. Why does SSCs only measure in the slot? If the PD current flows through the complete winding.
Yes, absolutely. In fact, the questioner is given a perfectly good thing. The PD signals, in fact, are transmitted through the entire winding and radiated in addition. The thing is, it's not just the SSC that's important here. The SSC is just nothing more than a broadband 10 megahertz to 1 gigahertz bandwidth antenna. It's a dual port electromagnetic coupler. That's how it works, okay? And it does see all sorts of other signals. If you actually look at the noise, you would see 99% of the signals that are picked up by the SSCs are discarded, okay? The reason is because in the instrumentation, we separate, the whole idea was to improve this signal noise ratio. When I first started putting capacitive sensors and using that 2 sensors per phase thing on our turbo generators in the old Ontario Hydro, we found there was all sorts of arcing and sparking coming from the machine, from the power system rather, that in fact we could easily get rid of using 2 sensors. But when I had signals coming from the machines, it turns out we also got arcing and sparking because of maybe a poorly torqued bolt on one of the flexible leads right near where the PD sensor is, and or arcing and sparking from stator core lamination. So we had what we called internal noise. And we developed the SSC because on the big, large hydrogen-cooled machines, we could put the sensor right inside the slot where the PD was most likely to be, okay? And it allowed us to get rid of all the harmless arcing and sparking from the machine terminals that the two sensor per phase method did not get on the machine terminals, could not separate out. There are lots of signals occurring, both from the power system and within the generator, have nothing to do with PD. And how we separate what's stator PD, caused by loose windings or contamination of the winding, those are the two things we mainly find in large hydrogen-cooled machines, is that we would look at the shape of the pulse. And again, I skirted over this in the beginning, but for us, when we detect a pulse from an SSC, we look at the shape. We look that it's basically a unipolar pulse, there's very little ringing, and we make sure that the width of that pulse is less than 6 nanoseconds. In other words, the rise time is less than 3 nanoseconds, because we know in hydrogen-cooled machines, that's the shape of the true pulse as detected by the sensor, okay? Now, if you have signals from another slot, what happens, so if you have PD in an adjacent slot, that PD is going to travel out the slot, out into the M winding. It's going to see a characteristic impedance mismatch there. It's going to see the inductance of the M winding. It's going to see the capacitance to the other coils in that M winding. And some of that signal from that slot, that PD in the other slot, one where you don't have an SSC, for example, will then come into the slot that you are monitoring. And now all of a sudden, the pulse is highly oscillatory. The width of the pulse is greater than 8 nanoseconds. This was all part of the $2 million R&D project we did when I was still at the utility to investigate exactly what the characteristics of the shapes of the pulses are. And so the electronics automatically separates the pulses between stator PD, which is a very characteristic thing, non-oscillatory, and a width less than 6 nanoseconds or so, and all the other kinds of pulses that are from either noise pulses or PD from other slots. And that, unfortunately, and we're using the impedance mismatches and the traveling wave phenomena that happens in a stator winding to do that. The bottom line is that is the SSCs will only, although it'll see signals from the rest of the machine, it will in fact only decode as stator PD the signals in that slot, because they're the only ones that are going to be non-oscillatory and very brief, that haven't gone through all the impedance mismatches and resonances and all that kind of stuff. So I hope that answers the question. They're absolutely right. Each SSC will see all the other signals that are conducted in from the M winding and from other slots, but by the way we digitally decode each pulse, we will classify that as stator PD or other kinds of noise. And those of you who are using one of our instruments called the TJS, you will know you can also create plots of wide pulses, okay, noise pulses, and invalid pulses. And these are all different kinds of noise pulses that are there. But to be sure, we can only detect that PD in that slot correctly. Everything else might be noise. Sorry, I don't give slow or short answers. You should see my arms, they're waving like crazy here. Next question. Or is there a next one?
Yeah, no, another one, yeah, for you. That's me find exactly where I am. Can the entire length of the winding be assessed by line couplers? Does the attenuation hinder the magnitude?
Okay, the reality is no, okay? As I tried to address a little bit earlier, and I encourage you, because I'll be giving a presentation, I think it's next, in August. I've already given it once or twice, low frequency versus very high frequency PD detection. But you might remember I showed you a slide a little while ago that talked about, well, if you're in the low frequency range, you should be able to see deeper in the winding with low frequency because there's less inductive impedance there. It turns out that that is a generally true statement, and at higher frequencies you're going to see less of the winding. But actually, what determines in online testing, what determines how much of the winding you're going to see is the voltage on those coils. Because remember, the very beginning of my presentation, PD is affected by voltage. Unless you have that high electric stress there, no matter how deteriorated that insulation is, it will not have PD. You will not get that little electric breakdown because there's no void to have it in, okay? And epoxy mic itself won't break down. So the issue here is, if you have a winding, say it's an 11 kV machine, so it's 6.6 kV or 6.3 kV between line and neutral, and say you had 10 coils between the line and neutral, that means the line end connected coil is operating at 6.3 kV. The next one's operating at 5.6 kV. The third coil down is operating at 5 kV. The voltage is going down linearly from line end to neutral. And there will be a point where, one, the PD won't occur, and anyone who's done any offline testing knows as you increase the voltage, you will get a dramatic increase, at least with the square of voltage, you will get a dramatic increase in the PD magnitudes. So all the high PD stuff happens in the line end terminals anyway. And this is why I really encourage you, if you can listen to this other Jazz, I think you're the one who's hosting it, if you're on here, that I have a low frequency versus very high frequency thing, where of course I use some of the data I have from many years ago, but I also show this data by Matthew Lachance that he just published last week for those of you who can access IEEE papers, and very clearly shows there's when you actually inject pulses in the VHF range, there's actually very little attenuation. In fact, I found more than what he did, but there's very little attenuation between the neutral end and the high voltage end. And the reason for that is because at the high frequencies, at the 100 megahertz frequency, the capacitance between the coils and the M winding, it is really, really relatively high. Therefore, the capacitive impedance 1/2 pi FC at high frequencies, that capacitive impedance is very low, and the PD just skips along the M winding, okay? And that's why we see relatively little attenuation, okay? And I know this really gets into the commercial domain. I want to remind everyone, we do both systems, so I'll do whatever you want, okay? But the reality is, if you look at it in the very high frequency range, there's relatively little attenuation compared from working in the low frequency region, where because of not attenuation, but natural frequencies, filtering effects, in the low frequency region, you can get dramatic changes in amplitude. Deeper in the winding, you can be, 2 or 3 coils in the winding, you can either detect nothing or huge signals depending on the frequency you're looking at. Okay, and I encourage you to look at that EIC paper, or join me for the low frequency versus very high frequency webinar that I'll be doing via Qualitrol in August. Okay.
Okay.
Any other questions?
Yes, I've got something else for this. They're catching up here. Let me just see the next one here. Here we go again. A Prpd pattern between 0 and 90 degrees with no specific amplitude at 45 degrees. Is that seen as classic PD?
Okay. Yes, that would be classic phase to earth or phase to ground PD. Okay. Because if you do simple experiments, which I did when I was studying PD when I was still in school, and or take a formal course of why PD occurs at certain parts of the AC cycle, if you have PD that is occurring between 0 and 90 degrees, that would be negative. That would be negative pulses, or between 180 and 270 degrees of the AC cycle, that would be positive pulses. That is probably almost certainly driven by the phase to ground voltage. So it's PD that's occurring in the slot or the immediate M winding. Okay, because remember the ground just extends a little bit beyond the edge of the slot, and the industry tends to call that classic PD. So when we say the word classic, it tends to mean it's driven by the phase to ground voltage. as opposed to PD that can occur in the M winding. You remember that GE winding? I probably shouldn't have said the brand name, but everyone can recognize the color. That blue winding where the PD was occurring between the coils because of inadequate spacing there. That is driven by the phase-to-phase voltage. So that's phase shift, either plus 30 degrees or minus 30 degrees from that 45-degree position, okay? And as a result, we've created a specialized, what we call ABC Prpd plots to allow us to do some phase shifting on B and C phases so we can see what's phase-to-phase PD and what's the classic PD that's just in the slot. Okay, so but the classic PD could still be caused by PD or voids rather right next to the copper conductors. It could be within the ground wall, that's normally thermal deterioration, or it could be still on the surface of the coil because the coils are vibrating in the slot, okay, causing slot discharge. All of those we call classic because of their phase position. Thank you.
All right. Well, Jazz has answered it. The other side that you're saying. If anyone's interested, we will be running a webinar on low frequency versus very high frequency on Tuesday, the 18th of August, and you can register on the IRIS website. And if you're having problems, you can contact me. I'll put you in the right direction. That's Neil.
Yes, I apologize. I'm doing so many webinars, I get mixed up, and I can't remember when they're happening anymore.
There we go.
But with that one, I draw information from other researchers and stuff, and I talk a lot more about pulse propagation in the windings. But there are a number of papers in there, and I encourage you also to read the IEEE and IEC standards. There's lots of discussion of that there also. Okay, but it's a very complicated situation. Any more? I guess we're getting close to the end. Oh, okay.
Do system voltages have any effect on PD and end winding vibration? E.g., what about low voltage random wound machines?
Okay. I hope I'm understanding it. I already talked about for form wound machines, those normally 3.3 kV and above. We have developed tables, and you'll see that we have different alert levels based on the voltage class if you're using a Vhf technology. If you're dealing with random wound machines, if it's fed from the normal power system from a conventional 50 hertz, you just plug it into the wall, okay? And most random wound machines are 690 volts and below. Not always, there's always exceptions, but 690 volts and below, they tend to be random wound. And if you're driven by sinusoidal voltage, the answer is no. There will be no PD occurring there, okay? It just will not occur, and there's no sense in doing PD measurements, and there's no sense in doing it either offline or online, okay? Now, if you're connected to a drive, however, the situation changes. Back in the late 80s and the early 90s, when the first modern type of voltage source PWM, that's pulse width modulated converters or variable speed drives, were introduced to the market, we were finding machine failures, stator winding failures, because now you're fed by that drive. The stator winding was now seeing all sorts of voltage impulses from the electronic switching within the drive, and it was initiating partial discharges because the voltages that were appearing, especially between turns, was much, much higher than it would see, the few volts it would see in normal operation under a sinusoidal application. So there, we have the issue that PD can cause failure. But because we're not usually using mica on random wound machines, it's really film insulation, okay? It turns out the polyamide-imide films that are most commonly used as magnet wire, as winding wire, do not produce, are not PD resistant. It's like polyethylene cable. It's like a hot knife through butter. If you've got any discharges, you fail usually within days, weeks, or a few months, certainly within warranty. And so beginning in the early 1990s, myself and many other researchers were investigating this, and we were asked by our customers, you know, because most OEMs of motors and generators also use our equipment in the factory. I said, hey, when I hooked up your PD detector to do a QA test, because I've heard about this PD thing, your detector failed. Okay, and it wouldn't have done it if it was normal 50 hertz voltage, but with these voltage pulses from an inverter, it basically produced high frequency signals that would zip right through the capacitors and blow up the electronics. And so we got involved in developing specialized PD detectors that can be used on the low voltage random wound machines. So this is motors, also wind turbine generators, where you want to measure the PD. And although I have another whole separate presentation on it, I think for those of you, the person who asked this question, they should be aware of a couple of IEC standards that came out on this, because this was a big issue. And we addressed it through making windings more reliable or resistant to PD, or making sure they don't have PD under inverter situations. So the standards you might want to look at are IEC 60034-18-41, that's for random wound machines, and IEC 60034-18-42 for form wound machines. And in -41, what you're supposed to do is make sure the partial discharge inception voltage is above essentially any expected voltage impulse you get from your drive, okay? So I hope that was the question you were asking. To me, it isn't so much a voltage issue, it's are you fed by an inverter? And it doesn't matter whether it's a low voltage motor, for a random wound, or if it's a higher voltage. There are now 85 megawatt motors out there that are fed by inverters and are having issues. But keep your eye on our website. That would be irispower.com, because I'm pretty sure I'm giving some discussions, or Connor Chan, one of my colleagues, will be giving one on that specific issue, where we can deal with it directly. Okay.
Okay, Greg, we got one more here.
Okay, and maybe we'll make this one the last question, but what I promise to do, if you send Neil or the SAIEE folks the questions, they'll get them to me and I'll do my best to answer them. It might take me a week or so because of other things I'm doing, but I will get back to you, okay? Yes, okay, the last question.
Okay, last question. What gap would you recommend between the end winding of a machine as PD is experienced on a poor formed coils, voltage
Okay.
66, 11, 15K? Seen
Okay.
damage in a short period of time, within 3 years.
Yes, but it might still take a decade to cause failure. The short answer is read my book because I get into that and I have references to other papers. It's hard to give a rule of thumb. In the olden days, I just said if I couldn't get my index finger between the coils on a 13.8 kV winding, the windings and between the coils at the phase break, when we had a A-phase coil right up against a B-phase coil in the M winding. If I couldn't get my finger between them, then it was too close. But things have been gradually changing over the years, because, and this is why I can't give just a simple answer, why I have to refer to the 2014 version of my book, is that the problem is generally speaking, most manufacturers of machines have been making their ground wall thinner. Or another way of looking at it, they've gone from an average design stress of, say, somewhere around 2 to 2.5 kV per millimeter thickness of insulation, up to 2.5 to 3 kV, and there's even some cases that go higher. And if you do a proper electric field simulation of the electric stress out there, you will find that as the insulation ground wall, main wall, gets thinner in the M winding, the more stress it puts on the air gap between the coils, and therefore the greater the probability of partial discharges in the M winding. Okay, so if you're dealing with a machine that's 30 years old, you would need, say, 4 or 5 millimeters minimum all along the whole length of the coil to make sure you didn't get into PD between the coils. This is on an 11 kV machine, okay? But nowadays, you'd actually need not 4 or 5 millimeters, but you need 6 or 7 millimeters, because more modern machines, okay, this wouldn't be rewinds, but this would be more modern machines, new machines, they probably have a thinner ground wall, and so you need more spacing there. So it depends obviously on the voltage level. The higher the voltage, the rated voltage of the machine, the bigger the spacing you need in the M winding, but it also depends on the thickness of the ground insulation. Okay, and because I know there are machines operating at higher altitude, once you get above 1,000 meters above sea level, that also causes further issues. Okay, because essentially the breakdown strength of air decreases as the pressure decreases. Okay, and so it exacerbates, makes the problem worse. But that was a good question, but I can't give a single number. I encourage you to read my book and more correctly the papers that have been published by various manufacturers over the years on how they calculate the electric stresses in the M winding, and therefore what spacings they need. There's not just a simple answer, unfortunately. Okay, Neil, I think we should wrap up. Because one, I want my lunch, and I have another webinar to do at 1 o'clock on condition monitoring in general.
I'd just like to say thanks, Greg. Thanks very much. Thanks for the chatting on that side. And we'd like to thank you all for attending and everything on that.
And thanks to all the attendees here today. I know listening to webinars is difficult and it's hard for good two-way communication. And I hope to be in South Africa again in maybe April of 2021. Hopefully the world will be a much safer place by then. So thank you very much and goodbye.
Okay, thanks, Greg. Thank you very much, and thanks to all your attendees. That's it. We will have this as a recording on the SAIEE website, and you can have a look at it on upcoming webinars. Enjoy your evening. Thank you very much.